Ooh. Hello, Lina.
Hi, doctor.
How are you?
I'm good. How are you, doctor?
Very good. Thank you. Hello, Kia. Hello, Lola. Hello, Sarah. Hello, Steven. Okay. Yeah, let's. And Boston maybe join different link. Are you connecting to the link that ends with 1.8?
It was ending with 6.7.
Okay. I'll quickly.
Yes, 6.7.
6. Okay. Boston link ends with 6.7. Okay. And maybe I can just share the explicit link with him. Oh, he's here. Okay, very good. Whew, happy to see, and I consider our meeting as a relaxation and relief. I'm like a little squirrel in the view. Was doing a couple of other meetings, but now it will be pleasant part. So let's chat a little bit, and then I'll start sharing slides. So how do you feel about homework? Is it too hard and too stressful, or it is doable?
Long.
Huh?
Long.
Oh, okay.
I haven't tried completely yet, but looking to the steps, and it seems like needed a lot of work.
I already tried, but few things I'm not able to understand.
Send me more questions. I'll try to address. I was answering a couple of questions, but send more.
Yeah, I know you already sent me so many things, but still, I already complete few stuff, but I have a portion after that.
So in several previous years, I was trying to make life of class attendees easier, and I skipped this assignment of doing periodic boxes. Then everyone was happy, but at the end of the class, most of class attendees were not able to do it for the projects. So I think I understand that it's a little bit of suffering. It's hard, but later on it will be benefits, especially to those of you who are planning to practice periodic structures like polymers or solid state. And so it is not. I'm not going. It's not my goal to make your life harder. I will be happy to remove this task completely and do just little molecules, which will be a little quicker. But what you're doing will be big help for the projects. And if it is completely undoable, do not panic. For the projects, when you need to do at least like 1 or 2 systems, I will assist and make sure that your systems are working. Just if in general we get a context of creating these periodic models and adding vacuum, it will be easier. Yeah, okay, I'll get the message. So if you can complete this homework before we start next lab, it will be really great. So that then we will continue to move on, building on the top of that. If by some reason you're able to complete, of course, we can complement what is missing during the lab, but then it will slow down our progress in the course and the time when we start the projects. So it is, I'm fine either way. I will not. I'm not going to give you a hard time. It's just if we all decide to move towards projects, it seems reasonable. So, what are we looking to do today? So, we basically finished Hardy-Fock and we are about to start DFT. And DFT is the workhorse of any materials simulations, but between these two, there is one transitional subject. And I believe today's meeting will be relatively easy because the subject that we are going to cover is quite close to your hearts, brains, and hands. So we will cover the stuff that you have already done several times in the homeworks. So we'll discuss the subject of ionization, energy, electron affinity, where it comes from. So some of you were complementing the homeworks with a paragraph from textbook or Wikipedia explaining what is Koopman's theorem. Koopman's theorem. If you haven't done it today, it will be part of the class.
Koopman's theory.
Koopman's theorem, like in,
Okay.
Also, so the overall name for today's meeting, for today's academic part of the meeting, will be observables. So in the following sense, when we build models and run computational chemistry software, what we are getting basically it's like orbitals, wave functions, and total energy. So basically, in narrow sense, all theories are designed to compute total energy. But in our experimental life, and if you're not speaking, please try to mute microphone. When it's needed, I'll happily mute myself and give you a chance just so that we do not get feedback. Thank you. Thank you. So I do not essentially have experimental life, and which I regret, but some of you have access to cool instruments and do experiments, and you know that one is getting a variety of results and types of results, observables. So one can measure spectra, conductivity. If you do electrochemistry, you basically measure ionization and affinity. One can get a lot of structural information. So there is, it would be different subject to mention all experiments. And one needs a connection. One needs a bridge between computations and real life, right? And this bridge between computations and real life is observables. So if you were taking quantum theory to some extent, then this concept is probably was a required part of the course. If you don't, we'll cover it here, but in the quantum theory, there is a concept of observables, which is also one of the postulates of quantum mechanics. Basically, if you have an operator corresponding to observable and you have a wave function, how to predict outcome of the measurement, right? So the stuff that we are going to do today will be similar to that. If we have completed Hardy-Fock calculation and we know specific features of a molecule and experiment, how we extract it from calculations. So you already know the answer in a practical sense. You know how to scroll throughout through .log file and find, for example, affinity and ionization, right? But in rigorous mathematical sense, we didn't prove that those results are helpful and they are correct. We need to discuss how how one can justify that what we are taking is comparable to experiment on one hand. On another hand, in the subsequent parts of the course, in the future, we will need to focus on one of the most interesting and pleasant part of the science, at least from my personal perspective, the interaction between matter and electromagnetic radiation. So this subject, it may sound a little challenging. I will start sharing slides after I'm done this little introduction. And talking is more important than, I believe, than actual slides. So interaction of light with matter is a general word for any spectroscopy, visible, infrared, microwave, NMR, rotational, vibrational, electronic, so X-ray. So in some sense, most of experimental probes in the instruments fit this interaction of light with matter or electromagnetic radiation with matter. And for this interaction, there are also specific observables that we need to start discussing today. So we need to do first steps towards interaction of light with matter. And the third thing that we will cover today will be the a very introductory background of periodicity. So the stuff that you're already practically doing in your present homework that we did in our previous lab. So how to think about periodic models, crystals and polymers. So some background ideas. So if you have questions, unmute your microphone and start asking, and I will start bringing up the slides. It will take, I hope, less than a minute. Okay. I have it, but and let me share it. But I am seeking for a little bit better version of. No, let's do it whatever we have. Otherwise, we'll lose time. So, do you see the slides? Please show yes or no.
Yes.
Okay. Yeah. Thank you. And in previous years, I was already at this point starting discussing research projects. So comparison to experiment, observables. So we need to look at this little blue box. Let's skip. So we are done with Hartree-Fock theory. since last time. And now let's look on several aspects. So first, let me ask what you see on this slide and how you interpret it. May I ask Lina?
Yes. So I see light wave, which is the electric field perpendicular to the magnetic field, which is and this is the equation that expresses the electric field.
Okay. Does everyone agrees with it? Are there any additional comments? Or please show if it is sufficient or if I need to give more comments. Yeah, thank you. Thank you. Kia, are you okay with this explanation or more is needed? Oh, okay. I think you decided to type more comments. Okay. Boston, would you like to give more comments?
Well, it just looks like you are depicting an electromagnetic wave, giving explicitly just the electric part of the field, not the magnetic part. In that wave, you're expressing it as a complex wave rather than as like a sinusoid. Well, it is a sinusoid, but complex one. Where k is the wave vector, omega is the frequency, and then you have the phi as the phase shift with the amplitude given by epsilon naught.
Okay. So I believe, so if there are more questions, Stephen, are you fine with it or more explanation is needed?
I'm fine with it.
Okay. So Kia, if you need more, these arrows are strengths of electric field that moves charges and magnetic field that rotates the arrow of compass. And if there is a source of electromagnetic radiation, these fields in a certain point of space are oscillating. Or if one looks through the range of space, then they're also oscillating. So in time and space. Okay.
So from that, we are what we are looking for.
So we
from
are,
this.
yes, we are looking to explore a molecule, right?
Mm-hmm.
That is being irradiated by light. The intuitive expectations are that the oscillations, light, electromagnetic radiation, light, so one can photoexcite molecule and promote electron between states on one hand. On another, if these oscillations of electric field are very slow, then it may induce polarization of a molecule if those are in like microwave. Or so there are some changes to like positions of ions and electronic clouds, because in the molecule electrons are attracted by ions, right?
Yeah.
But if we add external electric field, electrons want to please this field. Wherever a field directs, electrons will move or respond to electric field. And I'm not going to convert our class into physics class, but response of materials to external electromagnetic irradiation is an integral part of any material science. We cannot live without it. Make sense?
Yeah, it's okay.
Yep. Thank you. Now, let me ask Stephen, how do you interpret this slide, especially the stuff in this circle? I apologize for ugly drawing, but any comments or any? Of course, you can say it is some unreadable garbage, but anything behind that?
It appears to be measuring or depicting the electric dipole moment of a specific molecule in relation to time.
Okay, good. Thank you. Most of molecules are neutral. So amount of positive and negative charges, electrons and ionic charges are compensated. So if there would be ions in electrolyte, then electric field makes them to move, right? But if the molecules are neutral, then electric field will not move them. They will stay wherever they are. But if the molecule is polar, if it has dipole moment, electric field will make to reorient. Okay, and please stop me anytime if more comments are needed. So electric field reorients molecule, makes it to rotate until the line which connects positive and negative, which is also called dipole. So until this line will be oriented with the direction of electric field. If this angle between these two lines is non-zero, then the system of electric field and molecule will be unstable. So it will be some increment in energy. As soon as this arrows will be parallel, the energy will be minimal. Kaya, would you interpret it? Would you tell how you interpret this last statement?
Which one, Professor?
The idea about alignment between dipole and electric field.
Sorry, Professor, this time I'm not able to say anything because I don't have enough knowledge about this.
But just what you how you interpret it, not the knowledge, but impression, what you hear and interpretation. So what is dipole? Would you please try?
Professor, I think it's better if you explain.
So dipole is the line that connects positive charge with negative charge. Okay.
Yeah.
And the dipole is equal to the length of this arrow times the amount of the charge. So if you have positions of positive and negative, R plus, R minus, then the dipole will be equal R plus minus R minus time, and we assume that they have the same charge times the charge of this particles or average charge of a molecule.
So dipole is like a bond between two charges.
It's not wrong. Typically, one speaks different languages, but yes, bond between two charges or lengths of bond between two charges.
Okay. Yeah, when you draw, then I think that this one will be dipole.
Now,
means bond between
which, let me ask you the following. So suppose we have electric field oriented upwards, and then the dipole oriented at 90 degrees. Here D, here E. So it is situation number 1, and here is situation number 2. Electric field is again in the same direction, and dipole is going in the same direction. So which situation is energetically more favorable? So this is question for Kaya. Where the energy will be bigger, where the energy will be smaller.
The second one is bigger.
First one is bigger, I don't know.
First one is bigger, second one is smaller.
Yes.
So here is convention. Energetically favorable means smaller energy. So dipole wants to orient along the field. And same when you become a tourist and walk in the forest with a compass, the arrow of compass follows the magnetic field, right? Arrow of dipole follows the electric field, which means we can call this parallel, and this we can call perpendicular. So energy of perpendicular will be bigger than energy of parallel. Okay?
Yeah.
Good. Now, I'm going to say something relatively simple, but if you were not analyzing this aspect of material world, just be alert. It will be simple, but new. So let's convert this little exercise into purely mathematical form. So suppose we do have total energy operator of a molecule, which we use like a Hamiltonian in molecular Schrödinger equation. We were assuming that the molecule is isolated. So it is a universe which has only one molecule and a vacuum around, right? The whole universe consists of only one, titanium dioxide molecule. And there are no stars, no planets, only one molecule. But now we consider a little bit more complicated universe where there is a homogeneous electric field. And the molecule has a dipole. So how would total energy, how would the Hamiltonian of the molecule change in presence of electric field? Sarah, would you like to try?
Excuse me, can you repeat the question again?
Yes. So suppose we know a Hamiltonian total energy operator of a molecule in a vacuum. Now, to this vacuum, we add strong electric field. And we also suppose that it is a polar molecule with non-zero dipole. How the total energy will change?
I think the total energy will increase, yeah, because we insert another electron to the system.
So electric field is not an electron. It is a field which is introduced at each point of space, right?
Oh,
and
okay.
The answer of the equation, which is also shown in this slide, but the answer just interprets this little thing that we just discussed. So the change of the total energy will depend on mutual orientation of the field and the dipole of a molecule. So if we rotate the molecule in space, for example, with Gauss field, the energy will change.
Yeah, that's true.
Okay?
Yeah, yes.
So Sarah, you may just repeat the answer of Kea. In which situation energy will be bigger? When it is perpendicular or when it is parallel?
The first one, the perpendicular.
Has bigger energy, correct.
Yes.
Now, thank you. What if the angle is neither 90 nor 0 degree? If it has some like 45 or 30 or whatever. So some angle theta. So there is a way to say that the energy will be energy contribution, let's say energy prime, will be value of dipole times absolute value of electric field times cosine of this angle. And this equation, cosine of 0 will be 1, so it will be maximum. And it will not match our intuitive expectations. So we need to add minus sign. So minus cosine. So when they are parallel, energy is minimal. When it is 90 degrees, it increases, right? So this contribution is often written as scalar product of vectors. Vector mu dot product by vector e. And since we introduced the minus, we should put it, we should keep it. Make sense? Kay, would you share your impression, like how dot product of two vectors relate to polar molecule in electric field?
God.
It's just repetition of the same stuff we just discussed 5 minutes ago.
Yeah. Let me. If I'm wrong, then please, Professor, correct me because. Okay, so like if the angle is 90 degree, the dot product of the electric field will give you the maximum value.
Okay, I will correct later, but keep you're moving in the right direction. Keep going.
And actually, it's electric field totally depend on the angle between electric field and the dipole.
Correct. Energy depends on angle between electric
energy.
Yes, yep. Good enough. Thank you. So maximum value will be if the dipole will be directed against electric field. So if the dipole will be opposite direction, right? It will be bigger than 90 degrees. But if it is parallel, it is minimum. If it is 90 degrees, it is increase. And if it is opposite, it is maximum.
Yes. Yeah.
Are you happy with the dot product notation?
Yeah.
Okay. Anyone wants to criticize dot product notation? No one. Okay. Now, please follow me on watching this little blue box. So Hamiltonian equals Hamiltonian without interaction minus product of dipole times electric field. So it is Hamiltonian of a molecule in presence of electric field. And this dot product is energy of interaction between light and matter. Make sense? Steven? Are you okay with it? Okay, yeah, thank you. Let me quickly check that I have the right slides. I may have something a little bit better. Yes, I have the one with maybe edit. Different version. So Here we see absolutely the same equation, just typed better. Hamiltonian, non-interacting minus electric field, which depends on position in space, times dipole. The dipole can be defined, so dipole is an operator, can be defined as summation of all positions of ions for positive contribution minus summation of all positions of electrons for negative contributions, right? And now there is a little discomfort in the following sense. When it is hard to intuitively think of it, because we need to think not about one positive and one negative, but we have like several positive and several negative. And then the dipole will be arrow connecting average midpoint between all positive and midpoint between all negative. And number of positive and negative ions and electrons can be like hundreds, but the definition will work. Now, what I want to show, what is my goal? Suppose that I have some very oversimplified multi-electronic molecule, maybe something like H2, but I will not tell what it is. Just a molecule which has two orbitals filled with electrons. And I applied electromagnetic radiation of certain frequency to this molecule. And I want to observe that electromagnetic radiation will promote electron from occupied orbital E2. So we have two original occupied to virtual orbital E3. Okay. And in order to practice this consideration, I will have the following players in this game. I will have multi-electronic wave function in form of Slater determinant. And I will have an operator, which will be dipole that we just defined. And then the probability for this arrow, for this transition, that light promotes electron from occupied to unoccupied, should be proportional to the matrix element of this interaction. Please mute the microphone. I think someone is giving a little feedback. Thank you. And I will ask you to bring the microphones back for discussion. But so we are looking for matrix element of the Slater determinant corresponding to initial multi-electron determinant and final. And this initial and final determinants, initial and final multiple electron wave function will correspond to configurations. So initial is when we have, I will forget about spin and just draw electron as a little circle. So number 1 and number 2 are occupied with electrons, and number 3 is empty. So it is initial. And final, we will have number 1 occupied, number 2 empty, and number 3 occupied, because we promoted the electron from orbital 2 to orbital 3. Make sense? So we need to apply our knowledge, our machinery of equations that we developed for this situation. And do not worry, you did much more complicated considerations. This is not the highest challenge. Okay. So I am going to play to use the following things. So for the initial determinant or initial, I will use multi-electron wave function of 2 electrons, and they will be product of the first electron in orbital 1, second electron in orbital 2, right? So 1 and 2, and electron number 1 on first orbital, electron number 2 on second orbital. Although electrons are indistinguishable, and I need to cut this little image from our recordings, otherwise I will be fired. This is only little demonstration. Now, what would happen to multi-electron wave function upon we perform excitation? So electron number 1 will still be in the orbital number 1, and electron number 2 will be on electron number 3. So 1 in 1, electron number 2 in orbital 3. So this there are 2 products in the initial and final wave function, right? Okay. And here is our operator. So I'm going to practice this matrix element according to the following protocol. So in the matrix element, I will remove coordinates of ions because they are not getting changed if the electric field is changing quickly. So they will contribute only a constant to final answer, and it will be cancelled and removed. So I will keep only this portion, only electrons. So my operator will be identical to dipole operator for 2 electron system, and I can call mu. So it will be summation of position of electron 1 and position of electron 2. And probably I will skip doing vectors and do it only one-dimensional, otherwise it will be too much of writing. Okay? So I'm going to place this mu in the center of my sandwich between bra and cat. The actual bra and cat procedure will correspond to performing integration over R1 and R2. And my bra on one side will be this product of wave functions, bra, and this will be cat. So in bra and cat, and for bra, I probably should put star. So in bra and cat, first electron resides on the first orbital and doesn't change. But the second electron jumps from orbital 2 to orbital 3. So there is a difference between bra and cat before and after excitation. So here is the little exercise that I'm going to practice. Maybe at this point you already developed some level of irritation against the instructor for the specific purpose. It may not be clear why we need to torture our brains with this exercise. There was a general introduction that we will discuss interaction of light and matter, but it will be completely normal if by this point someone feels lost in transition. So please give me a little sign if maybe if a little reminder is needed, what is our expected goal, or when we will finish this torturing mathematical exercise. I see only smiles. So shall we, if you're okay as we go, or minus if we if I need to give a little. Okay, thank you, Sarah. So as you remember from 2 months that we are studying this subject that multi-electronic wave functions are a big challenge. And we achieved a great success of reducing multi-electronic wave functions into one electron mean field theory, which is Hartree-Fock. But now when we speak about observables, about a bridge to real world, we still see this multi-electron wave function, multi-electron operators, which we may hate because they're so complicated. So my main goal is to prove that one can practice one electron picture, even if telling by optical excitation of multi-electron system. So as a result of this consideration, in like less than 5 minutes, I will show that probability of transition can be expressed in terms of one electronic orbitals. So something will be much simplified in this expression. So it will be recast in terms of one electronic orbitals. So one can describe optical transitions in terms of one electronic orbitals with reasonable precision, reasonable qualitative accuracy. Whew. So, yeah, I think if one practices this expression, there is product, then summation, and then product again. If I open brackets, there will be 2 terms, and in each term there will be a product of 4 wave functions, right? In the first term, there will be phi1 R1, phi2 R2, then it will be R1, then will be phi1 R1, phi3 R2. And in the second term, it will be the same things, but in the middle will be R2. So let me show. Yeah, there is a ugly writing by hand, but I think this computer typing is better. So we open brackets, and we have phi1, phi2, phi1, phi3, and in the middle is R1. And the second term does have R2. And each term includes integration over R1 and R2. So why, and maybe it is the longest expression, the longest equation. Later on it will roll down here. Why do I need this relatively long mathematical expression? I want to practice orthogonality. We agree that atomic orbitals may be non-orthogonal, but molecular orbitals are orthogonal, right? So I'm going to use the property that phi1 is 1, but phi1 phi2 is 0. So, and anything else, when indices coincide, it will be 1, indices do not coincide, will be 0. So please help me to identify if there are any orthogonalities in the blue box. I didn't ask Lola about anything. Yes. Oh, would you like to help me with the blue box? So let me explain what I'm looking for and how to help me. I'm looking for a term that does not will not have R1, will have only wave function. I need to such term that includes integration over variable R2 and functions that depend only on R2. So would you guide me? What should I highlight? Like which function depends on R2?
phi2 star and phi3.
Thank you. And this phi without star R2, right? This one.
Yes, yeah, phi3 because this is
okay. Thank you. Thank you.
Oh, it should be phi2. Oh, okay.
Thank you, Laura. So I can take the yellow part out of bracket because integration over R2 and integration over R1 are independent. Those are independent variables, right? So out of the blue box, I can take this little yellow thing and it will read the following way: integral dr2 phi 2 star r2 times phi 3 without star r2. So, or in the Dirac notations, it will be phi 2 times convoluted with phi 3. What will be the answer of this?
0.
Zero, yes. Yes, correct. Thank you. So, and if one factor in the expression equals 0, then the whole box is equal 0, right?
Yeah.
So, what an easy life. It is twice as easier. Thank you all. You did help us to get through. Now,
No, it's me, Kia.
Kia, okay, Kia, please. Now you see in the second, in the red box, we do have R2 in the middle. And please.
It should be 1.
Yes, but please help me to highlight for everyone. Please help me to find those terms that will depend on R1.
Phi 1 star R1.
Okay.
And then there is phi 3.
No, depending on R1.
Okay. Depending phi 1 R1. And then it's equal to 1 because of optional vulnerability.
Exactly, thank you. So we are extracting this blue factor out of the blue box. And if you pardon me being short, it will be just phi 1 equals 1. Okay, yeah, thank you, Kia. Now, it means that I can completely cross through everything, this blue stuff. And we have substantially smaller number of terms. So we will have only, I'm out of colors. I didn't try, okay, this one. So I have only integration over R2, this wave function, this R2 in the middle, and this phi 3. Okay?
Yes.
And here is, I would say, the magic. So we started from finding matrix element of multi-electron wave function, but now we are coming just to a product of two one-electronic orbitals with position operator in the middle. And this trick can be done even if you have like 10, 20, 100,000 electrons. Only the electron that is traveling from one orbital to another one contributes to this probability of transition. The rest of electrons predominantly will give no contributions. And it is really wonderful result. So here one can call it matrix element between ground and excited. And basically we have better writing of it. Yes, so matrix element of position operator between orbital 2 and orbital 3. But most important that it is one electron matrix element. So I will switch the gears to a slightly different subject, but please consider to memorize it. We will come back to this derivation again and again through the course. It is something that we will need for course and for the project. Okay, now a little bit on the periodic models. So suppose we have a model that consists only of two atoms, but they are repeated again and again. So this little box is repeated, right? It is a repeating unit of a polymer. And I draw two atoms because I'm lazy. Typical models have a little bit bigger. So one can find the position of the same atom, like atom number one, in first cell and second cell, and subtract the vectors between them. So distance between the same atom in different replicas is called translation vector, right? And if you have the third replica, so the position of each atom in the next unit cell will be same as it was in the first cell plus translation vector. If you have the second cell, then it will be position in the first cell plus two translation vectors, right? And if it is not one-dimensional polymer, but two-dimensional, three-dimensional structure, then there will be translation vectors in each three directions, like A, B, and C. The general definition of the periodic structure is that potential nuclear to electron interaction in the shifted position and in the original unit cell are the same. So if you add the vector which is multiple of translation vector, the potential will stay the same. In a rigorous way, it is a definition of periodic model. Now the question, and in the following slide I will overview rather than derive. The question, how the periodicity of the model will reflect on properties of electrons, of electronic orbitals and electronic energies. So electronic, or like if you have positions of ions, then near each ion in the first cell, in the second cell, in the third cell, the potential, which is described here by red line, will be repeatedly the same. But the question is the blue line here. I can maybe highlight it with a different color. Blue line, which is electronic wave function. Will it be the same or different when we look on the next atom in the periodic cell, in the next cell? And there is a theorem after this Helix-Bloch that wave function will be the same by absolute value, but it will gain additional phase factor. It will be multiplied by a complex number, and this complex number will be repeat as we go through large number of the cells. So this thing in the box shows how the wave function or orbital will change if you move from one unit cell to its replica. So the part that is not getting changed often referred with this letter U and called atomic part, and the stuff that is getting accumulated as we go from cell to cell is related to plane wave electronic function. So it is a standard way to seek for orbitals or electronic functions in periodic solids. Okay, now I'm speeding up and I'm almost done. Now I will take the least time for most pleasant part. So do you remember this equation? You can show yes or no. Or please give signal, raise hand, or tell if someone doesn't remember this equation. So Boston supports Lina? No, okay. Then
I remember the concept and idea, but the equation I forgot actually.
but can you briefly tell what this equation is about? Or you can just read the title in front of you.
So as we dealt with single electron wave function for Hartree-Fock, it was summation over the electrons, but for total energy.
Okay.
So what is
So those are not orbitals, but orbitals energy, right?
Yeah.
And what is this J and K? I may swap the same, but so Sarah, would you like to help us? What are those pairwise contributions with two indices?
I'm not sure. Maybe they're referring to electron.
Yes, but if one electron is referred by one index, then which objects are referred by two indices? Just two electrons, right? And which energy corresponds to two electrons? Let's scroll through to the beginning of the lecture when we go over here. Yeah, it was, remember, we computed them through atomic functions. And I remember we were drawing Feynman diagrams for electron coming in and out, and having wave line between them, one diagram, and another was for electron was bypassing each other. What are the keywords for this J and K? The one who wrote in the chat line is correct. So let's try to remember this words. So how electrons interact with each other? Which law from classical physics?
Coulomb.
Correct.
And exchange.
Correct. So the one that goes here is Coulomb. The one where the swap is exchange. Okay. So Hartree-Fock energy is contributed by both single electron orbital energy and pairwise Coulombian exchange between pairs of all occupied orbitals. So we go from one to home, right?
So,
No.
Professor,
Yes.
Professor, one question. So, for Hartree-Fock, as I remember that it's the summation of like kinetic energy and potential energy of nuclei. Then after that, this Coulomb and exchange this one. So, but there, okay. So orbital energy, it's included kinetic energy and potential energy both. Okay, maybe.
Okay. Okay, I got your question, and if you give me a few minutes, I'll answer a question and complete the lecture. Both it is at no time. We do not have much left. So to the question of care, which we construct Fock operator, which includes this core energy, which indeed has kinetic gradient plus interaction with nucleus. Yes, but we want to formulate everything in a matrix form. Therefore, both core part and this Coulomb exchange are formulated in terms of matrix elements between orbitals, phi I and phi j. Or here, I think we call it mu and nu, but in terms of matrix elements. And if we already know matrix elements, then the energy will be just summation of these matrix elements between all pairs of orbitals. So original Hamiltonian, yes, it is expressed in the differential form, but now we have already converted our consideration from differential form to matrix form.
Okay.
And all considerations are now in goes as matrix elements. And now if we found orbitals and their eigenstates and matrix elements of the Coulomb exchange in terms of the molecular orbitals, then we can find total energy for all occupied orbitals. It will be energies of everything we occupied plus Coulomb exchange. No. Oh, I think I was answering it to someone else in the previous year.
Same question.
Now, we are going to make very big approximation, which is, some people may not forgive us this approximation, but it is needed for the sake of quick calculation. What if we just, for a short time, assume that Coulomb and exchange are approximately equal and do not change total energy much? This is very wrong. In practical situations, is a very big approximation. But for easy life, let's assume that temporarily we forget about them. Then total energy of a system that connects so many electrons, we need to add together energies of all occupied orbitals, right? Okay, and now we are going to discuss affinity, electron ionization and affinity. So about 3 years ago, there was a student, Christian News, who was delivering this ionization and affinity during his presentation for Gaussian, and I borrowed his slide. So here are orbitals, including HOMO and LUMO, and the ionization if one removes electron from HOMO, affinity if one places energy on LUMO. Right? And in fact, if one thinks from experimental point of view, ionization means that one looks for total energy of a system where number of electrons is reduced by 1. Or we physically removed electron, we ionized the molecule, right? Now, in the I'm showing 3 tables, and with ugly writing captions. Yeah, here is better. So in the central, it is neutral, and with total charge 0. We have occupied orbitals, and at each orbital we have 2 electrons, right? Then we have virtual, and we have no electrons. Now, if we remove 1 electron, we will, the easiest way to remove it, take it from HOMO, right? So if we change number of electrons by 1, if we actually remove electron. By the way, chemically, one can call it cation, charge +1. And in Gaussian calculation, you will need to put charge 1 instead of 0. So here on the former HOMO, we will have 1 electron instead of 2. And if you compute total energy of the system with number of electrons by 1 less, and subtract the total energy of the system with original number of electrons, this will be exact ionization energy, right? Now let's look on the affinity. If we, oh, sorry. Yeah, if we contribute an additional electron, it will be contributed to LUMO, right? So in HOMO there are 2 electrons, and in LUMO there is 1 instead of 0. And if the charge will be -1, in chemical language it will be anion, right? And the system, the molecule will have n+1 electrons. So we will need to look for subtraction between this total energy and this total energy for exact electron affinity. Now a little hocus pocus. So if we take approximation of Koopman, if we neglect Coulombian exchange, if total energy of system equals just to summation of all occupied orbitals, then for neutral, and I'm about to finish. If we are looking for total energy of a neutral molecule, we'll have energy of first orbital plus energy of second orbital. And in fact, we need to multiply by 2 if there are 2 electrons per orbital. But so going so forth, energy of orbital n-1, and then energy of the last orbital, where n is number of electrons. Make sense? Everyone is okay? Okay. Now, if I remove 1 electron, then total number of electrons will be -1, and total energy will be E1, E2, En-1, and then in place of E sub n will be 0. Correct? So if we subtract these 2 numbers, the difference will be equal to the energy of the orbital number n. So it will be electronic ionization approximately equals to energy of the HOMO orbital, right? So it is literally derived if we neglect Coulombian exchange. And the same trick for addition of an electron, for anion. So if we populate the LUMO, there will be contribution from orbital n+1, and we will have E1, E2, En-1, E sub n, and then E sub n+1. And if we subtract these 2, we will get energy n+1, which will be energy of LUMO orbital, which is I should go first. Ionization energy. Ionization energy, and here electron affinity. Make sense? Okay. Energy of HOMO, energy of LUMO. I think it is enough. Thank you for investing additional 15 minutes of your precious time over the limits. I invite everyone to consider lecture completed, and you're welcome to disconnect, and no one can leave the room except myself. But I'll stay connected just in case there are additional questions. And I'll send this slide. Sorry for not sending it before the lecture. Okay, meeting is done. If there are no questions and no one wants to disconnect, we can check about lecture summary. But I'm not insisting. It's up to you.
Have a good night, everybody.
Good night. Good night, Wolfgang. So Wolfgang doesn't want to summarize the lecture.
Yeah, I'd like to summarize, but I'm feeling so sleepy now.
Let's better invest time into relaxation.
Thanks, Doctor, for this interesting lecture. I enjoyed it, actually. Okay, good night, everyone. Bye.
Yeah, good night.
Thank you. Goodbye. Good night.
Good night, Lola. Good night, Sarah. Thank you.
Professor.
Yes. I know that Kia has questions. Let me check if Steven and Sarah have questions.
Just
Sarah does not. Steven, do you have any questions or discussion points?
oh, I forgot to use this phone.
It's okay. So I don't see questions from Steven. So okay, please go ahead with
Okay. Steven has some question.
No, he doesn't speak and doesn't type, which means likely either he doesn't have questions or there will be maybe there will be questions after he wants to be next.
After me, okay, maybe. Okay, so Professor, um, I have some question like my first question is that from that from that model, like just consider your last lab. So from first you showed one model like A, then you delete some atoms from the left side and right side.
Mm-hmm.
So why you delete those atoms? Like you delete those atoms because you want to uh, um, you want to create a atomic model like this way that could be continue like infinity. That's why. Just
Yes, you're absolutely correct. So I'm not telling about specific molecule. This is
yeah.
but suppose this is like I don't know oxygen and this is peroxide or maybe sulfur, and we want to make so here are terminal atoms.
Okay.
Which make bonds compensated and will prevent next blue atom to connect here. Right? But if I remove this atom and remove this atom, right, then I can consider that this bond and this bond are the same.
Yes.
So I need to remove terminal atoms to allow the connections through periodic boundaries.
Okay.
Make sense?
Still, maybe there is some lackings because I don't know so many things about this. But I don't know. I can't this time. This time I am not able to convince myself that. Still, now I have question like why we are deleting those atoms and how could I understand that atoms I need to delete.
Okay, so let's continue discussion, and I'm not running away from the question, but let's separate two things. First, practical aspects. So even if you disagree with procedure, please try to practice and do it. And second, intellectual understanding what's the reason behind this procedure. So for the homework, I'm asking you to complete, to just make it practical things.
Okay.
And I'm happy to continue the discussion, and if it doesn't sound logical, I will try to prove it. So We'll continue the same little toy. So suppose our elementary part has 2 atoms. Our unit cell has 2 atoms. Then in this little example, there are 4 atoms, right?
Yes.
So why do I need 4 if my minimal model consists has only 2?
Okay, now I understand. Now I got it. Okay.
So like this portion and this portion are identical.
Yes,
They're
yes.
replicas of each other.
Okay, okay. I got
So,
it. Okay, I get it now. Okay, I understand. Okay. So, Professor, one thing I want to show you, how to show you.
Oh, I need to make you co-host. Just a second.
Yes, yes, yes.
Make host, and just in case Steven needs to show something now or later, make Steven co-host as well. Okay.
Sure. Okay. So after that, okay, this one. So after that, we need to find homo lumo. If I am able to understand the homo lumo from this result, like this one is the most important part. This here we are able to see the bond number. It's a bond
orbital number. Orbital number.
Okay, orbital number. It's
So
a
you're
bond
asking
energy.
why there is 1 electron instead of 2, right?
No, my question is that it's bond number, bond energy, occupation. So from here, which one is homo lumo? How could I understand that? From the previous one, it was so easy because it's written, but here it's not written.
So the situation you are showing here is a little unusual, but you have the last that has electron and the first that doesn't have electron. So 18 and 19 will be your homo and lumo here.
So I'm correct. I identify like this. This one. This one is should be homo, and this one is lumo.
Yes.
Right?
Yes.
Okay. Okay. My concept is not on that time when I did. Actually, I did the whole homework yesterday, but okay, on that time I don't know, but it's correct. This one is homo and 1.53 is lumo.
Okay, and please show your periodic model.
Okay, periodic model means figure.
Yes, figure. Atomic. Yes.
Okay, so after removing this one is the main, like this one for second. There is 2. One is, I forgot the name. It's too complicated. Okay, this one is second one.
Acetylene and another is silicon nanowire.
Yeah, it's. Let me open this one. Okay, so this one for second one. You told us that we need to build 2 model. This one for second one. So this one before deleting the atoms, and this one is after.
Something is not right.
Yeah, maybe.
So on the terminal atoms, if you slowly move the mouse, very slowly, very slowly.
Okay.
Even slower, very slow. So now move it to the right. Move it to the right.
Professor, it's an image, so.
I understand.
Okay.
Slowly move the mouse to the right, not left, right.
Right.
Yes. Stop.
Okay.
So look on this silicon atom and tell me how many neighbors this silicon has.
So, Professor, there is 1, 2, 3, and 4.
Okay, 4 neighbors. How many neighbors are silicon and how many neighbors are hydrogens? How many yellow bonds and how many white bonds?
So, there is 2 yellow bond and should be two white bond, means a
Very,
hydrogen.
very good.
Yes.
Now slowly move the mouse to the
There?
Yes.
Yes.
Now for this atom, how many yellow bonds and how many white bonds?
From this one to that one is one yellow bond and there is 3 hydrogen.
But in the periodic model, why there are 3?
Oh, there should be, I need to remove another hydrogen.
Yes, yes.
I need to do the assignment again. Okay, it will not take too much time. Okay, I understand.
Mhm.
Okay.
Yep. Now I think you are you got
Yes.
the idea.
So, Professor, just check this one. This one for the first one.
So at the end also.
So
oh,
here
wait,
I need to.
wait.
Okay.
Wait. Did you read Wikipedia page about transpolaracetylene?
No.
No. So you are doing regular alkyl chain, which is also, it is okay for the class, but it is not as interesting scientifically. So
Okay.
here, each carbon has 4 neighbors, right?
Yes.
And we need each carbon to have 3 neighbors. So remove several hydrogens. Look on the Wikipedia article. So it should
Oh, no. You are talking about this, Professor. Actually, I saw the diagram in Wikipedia. You sent a link. I opened that one. So from there, they showed a figure. So there is silicon 1, 2, 3.
No,
There is 3 hydrogen.
If it is silicon, then you are
Yes.
fine. Are you talking about silicon or carbon?
No, it's the carbon.
For the carbon.
Yes.
Carbon,
for carbon, there is 1, 2, 3.
No.
No?
It will not affect the grade if you do not have.
No. It's not about affect the grade. It's about the understanding.
Okay, then let me tell. And Stephen, if you are here, maybe you can. Oh, he's not here.
I don't know he is here or not.
He is here. Stephen, would you, if you want, you may give some comment about conjugated polymers, if you want. If no, it is fine.
Let me open your homework.
Just the link to Wikipedia.
Yes, it's homework 7. Review for carbon, right? The first one.
Yes.
Yes. This one. So yeah.
So how many bonds each carbon has? Just based on this figure.
Based on this figure, 1. Because it's removed, so there still is 4. 1, 2, 3, 4.
Yes, carbon is 4 valent.
Yes.
But other double bonds here. Say yes, no. Okay.
Yes.
So physically, slowly move your mouse to one of the carbons, to one of the carbons. So you show double bonds, right? Double bonds.
Yes. And double bond.
If we symbolize double bond, for example, by thick stuff, it will be still a bond which is just has different lengths and is a little thicker, right?
Yeah.
Return back here. Return back to this one is good. This one is good. What you're showing.
Yeah, because the previous one, maybe I showed you the wrong one. This one is the after removing atoms.
Yes. Yes, this one is great.
Correct or not?
But it is not correct.
It's not correct.
Wait.
Oh, okay.
Yes, I'm thinking twice as slower. So how many carbons do you show here?
1, 2, 3, 4, 5.
And if your unit cell has 2 or 4 atoms, why there is 5? You need to remove 1 carbon either from the left and right. Yeah, maybe remove atoms 1 and 2, or 8 and 9. One of the, so maybe move to the left, slow.
Okay, this one?
If you remove atom number 1 and atom number 2, and then repeat exercise, then the result will be correct.
Okay.
And by
Okay.
the way, you are showing not trans polyacetylene, but you are showing cis polyacetylene, which is not bad. It is isomer, which has very similar properties.
Professor, why I did mistake? Because before talking with you, my concept was not clear. It's how I did this. It's like I consider this one is like a box. Then if I cut this section, then after that, if I like cut from the left side and right side, then if I match this one, then it goes to infinity like this way.
Okay.
But
Yeah,
it's also wrong.
so probably I believe you'll understand everything by now. But if you would start this subject now, or if you want to teach someone else,
Yes.
you can take the return back your image of the model.
Yeah.
Yeah, this one. Yes.
Okay.
So you can print it on a paper, several copies, like 3 copies.
Okay.
And then put the copies of paper on the top of each other. So when you shift this piece of paper, make a little offset, it should look like a continuous repeating pattern.
Okay.
Right?
Yeah. Now it makes crystal clear when you showed like that model, this one.
Okay.
From Wikipedia.
Since your project will be on polymers, I think for you it is critically important for your research.
Yes. Okay. So Professor, see you tomorrow. I will.
See you. I look forward.
Okay. Okay. Bye. Thank you so much.
Thank you. Stephen, are you connected by error or you have intention to discuss something? I assume you probably left the room and just kept it open. So I'm going to count to 3 and close the session. 1, closing session in 2 seconds. 2, closing session in 1 second. 3.